Welcome to this coding problem walkthrough. Today, we'll be tackling problem number 2197, replace non-Coprime numbers in array. This problem is a fascinating challenge that combines number theory and array manipulation. In this session, we're going to explore different approaches to solve the problem, analyze their efficiency, and gain a deeper understanding of the concepts involved. Let's dive in. The problem involves an array of integers called nums. The goal is to repeatedly examine pairs of consecutive elements in the array and replace them under a specific condition. If two consecutive numbers are not coprime, that is, their greatest common divisor, or GCD, is greater than 1, they are replaced with their least common multiple, or LCM. After replacing the pair, the array is shortened by removing the second element of the pair, and the process continues. This process is repeated until no more replacements can be made. Finally, the modified array is returned. Remember, two numbers are coprime if the only positive integer that divides both of them is 1, meaning their GCD equals 1. The input is a list of integers, and the output is the transformed array after applying these operations. Let's look at the first example to understand the process. The input array is 6, 4, 3, 2, 7, 6, 2. First, we check the pair 6 and 4. Since their GCD is 2, they are not coprime, so we replace them with their LCM, which is 12. The array becomes 12, 3, 2, 7, 6, 2. Next, we check 12 and 3. Their GCD is 3, so we replace them with their LCM, which is also 12. The array now becomes 12, 2, 7, 6, 2. Then, 12 and 2 are not coprime, so we replace them with their LCM of 12, resulting in 12, 7, 6, 2. The next pair, 7 and 6, are coprime as their GCD is 1, so no replacement occurs, and we move on. Finally, the pair 6 and 2 are not coprime, so we replace them with their LCM, which is 6. The final array is 12, 7, 6, and no further replacements are possible. In the second example, the input array is 2, 2, 1, 1, 3, 3, 3. Starting with the first pair, 2 and 2 are not coprime because their GCD is 2. Replacing them with their LCM of 2 gives the array 2, 1, 1, 3, 3, 3. Next, 2 and 1 are coprime as their GCD is 1, so we move to the next pair. The pair 1 and 1 are not coprime since their GCD is 1, so we replace them with their LCM, which is 1. This results in 2, 1, 3, 3, 3. Now, 3 and 3 are not coprime because their GCD is 3. Replacing them with their LCM, which is 3, gives us 2, 1, 3, 3. The process repeats for the final pair of 3 and 3, again replacing them with their LCM of 3, resulting in 2, 1, 3. At this point, no further replacements can be made, so the final array is 2, 1, 3. In the third example, the array starts as 8, 6, 9. The first pair, 8 and 6, are not coprime since their GCD is 2. We replace them with their LCM, which is 24, resulting in 24, 9. Next, 24 and 9 are also not coprime because their GCD is 3. Replacing them with their LCM of 72 gives the array 72. Since there is only one element left, no further replacements are possible, and the final result is 72. This example demonstrates how a series of replacements can condense the array into a single value when all elements are not coprime. Some important notes about the problem include the constraints and edge cases. The array can contain up to 100,000 elements, so the solution must be optimized for efficiency. Additionally, the values in the array can be as large as 100,000, meaning operations like GCD and LCM should be implemented carefully to avoid performance issues. Edge cases to consider include single-element arrays, where no replacements are possible, arrays where all elements are coprime, arrays where all elements are the same, and arrays with a mixture of coprime and non-coprime numbers. These scenarios help ensure the solution is both robust and efficient across a variety of inputs. To start, let's discuss the brute force approach. The intuition here is fairly straightforward. We iterate through the array, examine every pair of consecutive elements, and replace any non-coprime pair with their least common multiple, or LCM. This process is repeated for the entire array until no non-Coprime pairs remain. While this method is simple and easy to understand, it comes with significant performance drawbacks. Every time we replace a pair, the structure of the array changes, meaning we have to frequently recheck the entire array for new non-Coprime pairs. Additionally, the repeated computation of greatest common divisor, or GCD, and LCM for multiple pairs further adds to the inefficiency. As a result, the time complexity of this approach is n squared, in the worst case, because we might need to scan and rebuild the array repeatedly for every non-Coprime pair. This makes the brute force method impractical for larger arrays. Now, let's explore a more efficient way to solve the problem using a stack-based approach. The key insight here is that non-Coprime replacements only impact adjacent elements in the array. By utilizing a stack, we can efficiently manage these replacements while preserving the order of elements. Here's how it works: as we iterate through the array, each element is pushed onto the stack. Whenever there are at least two elements on the stack, we check the top two for non-coprimality by calculating their GCD. If their GCD is greater than 1, it means they're non-Coprime. In that case, we replace the top two elements with their LCM and repeat this process with the new top of the stack. This approach is efficient because it focuses only on adjacent pairs and avoids scanning the entire array repeatedly. A few key observations make this method effective. First, two numbers are non-Coprime if their GCD is greater than 1. Second, replacing these numbers with their LCM ensures that all divisors of both numbers are preserved. And finally, the stack structure naturally enforces the adjacency requirement, simplifying the process. In terms of complexity, this approach runs in an asterisk log, max, nums, where the log, max, nums, factor comes from the GCD computation. The space complexity is n, due to the stack. Having considered both methods, the chosen strategy is the stack-based approach because of its efficiency in both time and space. Unlike the brute force method, it avoids repeatedly scanning the array and focuses solely on elements that require merging. The stack structure simplifies the management of adjacent pairs, ensuring that operations remain efficient even for larger inputs. When comparing the two approaches, the brute force method is easier to implement but struggles with scalability due to its quadratic time complexity. On the other hand, the stack-based approach is slightly more complex to code but offers significantly better performance, especially for arrays with a large number of non-Coprime pairs. Both methods preserve the array's overall order, but the stack-based solution achieves this with far fewer redundant checks. Ultimately, the stack-based approach strikes the best balance between clarity, efficiency, and scalability, making it the most practical choice for solving this problem effectively. In this problem, we are tasked with processing an array to ensure that no consecutive numbers are non-Coprime. Two numbers are non-Coprime if their greatest common divisor, or GCD, is greater than 1. The solution involves repeatedly merging such pairs into their least common multiple, or LCM, until all pairs in the array are Coprime. To begin, we initialize the algorithm by defining the input array, which may already contain non-Coprime pairs. These pairs need to be resolved iteratively, step by step, to transform the array into its final stabilized form, where no further replacements are necessary. The core of the solution lies in iteratively replacing non-Coprime pairs. Starting from the first element, we traverse the array to check each consecutive pair. For a pair of numbers, we calculate their GCD. If the GCD is greater than 1, the pair is non-Coprime, and we replace them with their LCM. The LCM is calculated using the formula a*b //GCD a b. After merging, the second element of the pair is removed from the array since it is already included in the LCM. This process is repeated from the beginning of the array after every replacement, ensuring that all non-Coprime pairs are sequentially resolved. Once an entire traversal of the array results in no replacements, the array is considered stabilized, and the resulting sequence is returned. Understanding the key insights behind this algorithm is crucial. First, two numbers are Coprime when their GCD is 1, meaning they share no common factors other than 1. When a pair is non-Coprime, replacing it with its LCM ensures that the resulting number retains all the prime factors of the original pair, satisfying the problem's requirements. The iterative stabilization process guarantees correctness since the array is repeatedly processed until no unresolved pairs remain. From a complexity perspective, GCD computation is efficient, taking logarithmic time with respect to the smaller of the two numbers. LCM computation builds on this, while array traversal in the worst case can require multiple passes, leading to an overall complexity of O(n) squared for the brute force approach. The algorithm relies on fundamental data structures and functions. The array serves as the primary data structure, dynamically resizing as elements are removed during the merging process. This ensures that the sequence is updated efficiently at each step. Two key auxiliary functions are used. The GCD function determines whether two numbers are non-coprime, leveraging the Euclidean algorithm for logarithmic efficiency. The LCM function, which combines two numbers into their least common multiple, is directly built on the GCD function. Together, these tools enable the algorithm to process the array systematically and ensure correctness. To better understand how the algorithm works, let's walk through an example with the input array 6, 8, 3, 15. In the first pass, the pair 6, 8 has a GCD of 2, so it is non-coprime. We replace it with their LCM, which is 24, resulting in the array 24, 3, 15. Next, the pair 24, 3 is checked. Their GCD is 3, so they are also non-coprime. We replace them with their LCM, which is again 24, resulting in 24, 15. Finally, the pair 24, 15 has a GCD of 3, so it is replaced with their LCM, 120, leaving us with 120. At this point, the array is stabilized because it contains only one element, and the process stops. The final output for the example is 120, demonstrating how the array is resolved into its stabilized form. Let's now consider some edge cases. For a single element array like 7, the output remains 7, as no replacements are needed. If all the elements in the array are coprime, such as 5, 7, 11, the array remains unchanged. On the other hand, when all pairs are non-coprime, as in 4, 6, 8, the array resolves completely to a single number, 24. Finally, it is important to ensure that the algorithm handles large numbers efficiently, relying on the logarithmic complexity of GCD and LCM computations to process even large inputs effectively. This solution processes the input array nums iteratively to replace consecutive non-coprime numbers with their least common multiple, LCM. The key data structure used here is a stack, which helps efficiently manage the merging process. 1. Initialization. We start by importing GCD from the math module to calculate the greatest common divisor, and reduce from functools for potential use, though it's not applied here explicitly. The replace non-coprimes function is then defined under the solution class, following the LeetCode structure. 2. Stack setup. An empty list stack is initialized to keep track of the processed numbers as we iterate through the input array. 3. Main loop. For each number in the input array nums, we check if it is coprime with the top number in the stack. This is done using the GCD function. If the greatest common divisor is greater than 1, it means the numbers are not coprime. For merged non-coprime numbers, while the stack is not empty and the current number is non-coprime with the stack's top, we calculate the LCM of the two numbers. The formula for LCM is A*B //GCD A B. The number at the top of the stack is popped, and the resulting LCM is stored in the variable number. 5. Push result. The resulting number, either the current number or the LCM, is pushed back to the stack. This ensures the stack always contains numbers that are either coprime or need further merging. 6. Final result. Once all numbers are processed, the stack contains the final array after replacing all non-coprime numbers. This is returned as the output. This approach ensures that the array is processed in O(n*log, max, nums, time, where n is the length of the input array, and max, nums, is the maximum value in the array. This is efficient given the constraints. The stack structure ensures minimal reprocessing and simplifies managing the merging operations. Here, we begin with the Java implementation for solving the problem of replacing non-coprime numbers in an array. The solution is encapsulated within the replace non-coprimes method, which takes an integer array as input and returns a list of integers as the result. We start by initializing an empty list called stack to store the processed numbers. Then, we iterate through each number in the input array. For each number, we check if the stack is not empty and if the greatest common divisor, or GCD, of the top element in the stack and the current number is greater than 1. If this condition is true, it means the two numbers are not coprime, so we remove the top element from the stack and calculate the least common multiple, or LCM, of the two numbers. The result becomes the new number to process. This loop continues until the number is coprime with the top element of the stack or the stack becomes empty. Finally, the number is added to the stack, and after processing all elements, the stack is returned as the result. To support the main logic, we define two helper methods, GCD and LCM. The GCD method calculates the greatest common divisor of two integers using the Euclidean algorithm. It repeatedly replaces the larger number with the remainder of the two numbers until the remainder becomes 0, at which point the smaller number is the GCD. The LCM method then uses the GCD to calculate the least common multiple. The formula for LCM is the product of the two numbers divided by their GCD. This ensures that the LCM calculation is both efficient and accurate. Together, these methods provide the foundation for determining when two numbers are not coprime and for combining them into their least common multiple as part of the problem solution. In this first example, we start with the input array 6, 4, 3, 2, 7, 6, 2. The process begins by initializing an empty stack. When processing the first number, 6, we simply push it onto the stack, making the stack 6. Next, we process 4. The greatest common divisor, or GCD, of 6 and 4 is 2, which means these numbers are not coprime. Since they are not coprime, we calculate their least common multiple, or LCM, as 6 by 4, // 2 equals 12. We then replace 6 in the stack with 12, resulting in the stack 12. Moving forward to 3, the GCD of 12 and 3 is 3, so they are also not coprime. We calculate their LCM, which is 12 by 3, // 3 equals 12, and replace 12 in the stack with the same value, leaving the stack unchanged as 12. When we process 2, the GCD of 12 and 2 is 2, indicating they are not coprime. The LCM is 12 by 2, // 2 equals 12, so we again replace 12 with 12 in the stack, keeping it 12. Finally, we process 7. The GCD of 12 and 7 is 1, showing they are coprime, so we simply push 7 onto the stack, resulting in 12, 7. Now with the stack at 12, 7, we process the next number, 6. The GCD of 7 and 6 is 1, meaning they are coprime. As a result, we push 6 onto the stack, which now becomes 12, 7, 6. Next, we process 2. The GCD of 6 and 2 is 2, so these numbers are not coprime. We calculate their LCM, which is 6 by 2, // 2 equals 6. Since the LCM is the same as the value being replaced, the stack remains 12, 7, 6. At this point, we have finished processing all elements, and the final output for this example is 12, 7, 6. In the second example, the input array is 2, 2, 3, 3, 4, 6. As before, we start with an empty stack. The first number is 2, which we push onto the stack, resulting in 2. For the second 2, the GCD of the top of the stack, 2, and the current number, 2, is 2, meaning they are not coprime. We compute their LCM as 2 by 2, // 2 equals 2, and we replace 2 with 2 in the stack, leaving it unchanged as 2. Next, we process 3. The GCD of 2 and 3 is 1, so these numbers are coprime. We push 3 onto the stack, updating it to 2, 3. For the second 3, the GCD of 3 and 3 is 3, meaning they are not coprime. We calculate their LCM as 3 by 3, // 3 equals 3, and replace 3 in the stack with 3, leaving the stack as 2, 3. Now, we process 4. The GCD of 3 and 4 is 1, indicating they are coprime, so we push 4 onto the stack, resulting in 2, 3, 4. With the stack at 2, 3, 4, the next number to process is 6. The GCD of the top of the stack, 4, and 6 is 2, which means they are not coprime. We calculate their LCM as 4 by 6, // 2 equals 12, and replace 4 in the stack with 12. The stack is now 2, 3, 12. At this point, all elements have been processed, and the final output for this example is 2, 3, 12. Moving on to the third example, the input array is 8, 6, 9, 3. We start with an empty stack and process the first number, 8, by pushing it onto the stack, resulting in 8. Then we process 6. The GCD of 8 and 6 is 2, so they are not coprime. We calculate their LCM as 8 by 6 // 2 equals 24, and replace 8 in the stack with 24. The stack becomes 24. Next, we process 9. The GCD of 24 and 9 is 3, indicating they are not coprime. For 9, we calculate the LCM with 24 as 24 by 9 / 3 equals 72, and replace 24 in the stack with 72. The stack now contains 72. Finally, we process the last number, 3. The GCD of 72 and 3 is 3, which means they are not coprime. We compute their LCM as 72 by 3 / 3 equals 72, and replace 72 in the stack with the same value, leaving it 72. Since all numbers have now been processed, the final output for this example is 72. This completes the walkthrough of all examples, demonstrating how the non-coprime replacement process works step by step. The time complexity of our solution is influenced by the way we process the nums array and manage the stack operations. To start, consider the outer loop, where we iterate through each element in the array nums. If the array has n elements, this loop will naturally execute n times. Now, within this loop, there is a nested while loop that depends on the stack state and the greatest common divisor, or GCD, of the top stack element and the current number. The key observation here is that each element in the array can be pushed onto and popped from the stack at most once. Why? Because every time we compute the least common multiple, or LCM, during a pop operation, we effectively merge numbers, reducing the total number of elements in the stack. This means the total stack operations, pushing and popping, are bounded by O, n. Since the LCM computation involves a GCD calculation, we'll delve deeper into its cost next. The GCD computation is a fundamental part of our algorithm and operates in O, log, min, A, B, time, where A and B are the two numbers being compared. Given that the elements in the array can be as large as 10⁵, this introduces a logarithmic factor based on the size of the numbers. Now, if we consider the overall time complexity, the worst-case scenario occurs when every element in the array requires multiple stack operations. However, since the total stack operations are limited to O, n, and each GCD computation is O, log k, where k is the maximum value in the array, the total time complexity becomes O, n * log k. This balance between the stack operations and the logarithmic cost of GCD computations ensures an efficient solution. Turning our attention to space complexity, the primary factor is the stack used to store intermediate results. In the worst case, all elements from the input array could end up in the stack simultaneously, requiring O, n, space. Additionally, the GCD computation itself is efficient in terms of memory, using only O1 space. This is because the GCD function is implemented iteratively or with recursive tail call optimization. Lastly, the input array nums occupies O, n, space, but this is part of the input and not additional memory used by the algorithm. Combining these factors, the overall space complexity is determined primarily by the stack, resulting in a total space complexity of O, n. When comparing this optimized solution to a naive approach, the efficiency becomes even clearer. In a naive approach, we might check all pairs of elements in the array to identify non-coprime pairs and replace them iteratively. This would involve a time complexity of roughly O, n squared * log k, because of the repeated pairwise GCD calculations. In contrast, the optimized solution leverages a stack to process elements iteratively, ensuring that each element is pushed and popped at most once. This approach significantly reduces the time complexity to O, n * log k, making it much more scalable for large inputs. To further understand the efficiency of the given solution, let's break it down mathematically. The total number of stack operations, pushes and pops, is capped at 2n, as each number is pushed onto the stack once and popped at most once. Each GCD computation, which takes O, log k, time, contributes to the overall cost. Multiplying this by the O, n, stack operations gives a total GCD computation cost of O, n * log k. On the space side, the stack is the primary auxiliary structure, and its maximum size is O, n. Since no additional memory-intensive structures are used, the space complexity remains at O(n). In summary, the solution is highly efficient, with a time complexity of O(n*log k and a space complexity of O(n), making it a significant improvement over less optimized methods. When working on this problem, there are a few common mistakes to watch out for. First, an incorrect calculation of the least common multiple, or LCM, is a frequent issue. Many people use the formula LCM A, B equals *b / GCD A, B without considering the risk of integer overflow. This happens because the product of A and B can exceed the integer limit for large values, leading to incorrect results or runtime errors. To fix this, you can use Python's built-in math.lcm, which handles these cases automatically, or calculate the LCM as //GCD A, B *b to avoid overflow entirely. Another common mistake is failing to update the array in place. If you modify a copy of the array instead of the original during iteration, it can lead to discrepancies between your computed results and the expected output. Always ensure you're updating the original array or explicitly returning the modified version. Lastly, skipping rechecks after replacing a pair with their LCM is another pitfall. This can leave unresolved pairs in the array because the problem requires all consecutive elements to be coprime. To address this, you can use a stack-based approach or restart the iteration after each replacement to ensure that all constraints are met. Another frequent issue is implementing an inefficient brute force approach. Recomputing the GCD and LCM for all pairs in every iteration leads to redundant calculations, which significantly increases the time complexity. This can be avoided by optimizing the process, for example, using a stack to store intermediate results or leveraging memoization to reduce redundant work. Additionally, there's a common misunderstanding about the definition of coprime numbers. Some assume two numbers are coprime if they are both prime, but that's not true. Coprimality means the greatest common divisor, or GCD, of the two numbers is 1. This holds regardless of whether the numbers themselves are prime or not. Always use the GCD function to verify coprimality, rather than relying on assumptions about the number's primality. In interviews, this type of problem is an excellent opportunity to showcase your pattern recognition and problem-solving skills. You'll often see iterative replacement or stack-based processing as a recurring technique in array transformation problems. Being able to identify when to use a stack for efficient rechecking is a key insight. It's also important to discuss the trade-offs between different approaches. While a brute force method may be easier to implement initially, it's inefficient for larger arrays. Interviewers might expect you to analyze and compare both naive and optimized solutions. Be sure to address edge cases as well, like arrays where all elements are the same, arrays of size 1, or arrays containing very large prime numbers. Communication is also important. Clearly explaining why rechecking neighbors after replacements is necessary demonstrates your understanding of the problem constraints. You can also connect this problem to related ones, such as LeetCode 1979 for finding the greatest common divisor of an array, or LeetCode 1201, where reasoning about the LCM plays a central role. Problems like LeetCode 1447 and LeetCode 1250, which involve coprime checks and GCD-based logic, are also great to explore for further practice. There are several alternative approaches you can use to solve this problem, depending on the constraints and input size. A stack-based approach is one of the most efficient. Here, you iteratively process the array by pushing elements onto a stack. When the top two elements are not coprime, you replace them with their LCM and recheck. This method has a time complexity of O(n)log max_element and is faster than brute force, though it does require additional space for the stack. Another option is optimized in-place iteration, where you replace non-coprime pairs directly in the array and restart the iteration whenever changes occur. This approach is more space efficient, using only O(1) additional space, but it can be slower due to repeated iterations. For advanced use cases, you might consider a segment tree. This allows you to efficiently query and update GCDs in subarrays, making it suitable for processing larger arrays. However, it comes with higher implementation complexity. The best approach depends on the specific problem constraints, so it's essential to weigh the trade-offs carefully before choosing a solution. Thanks for following along. We wrapped up the problem by summarizing the key points and takeaways, including the importance of understanding coprime numbers and optimizing array operations. Don't forget to practice similar problems to strengthen your skills. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!